All right, so we are talking about something called arrays and slices. Arrays are actually well known to all people who do programming. Slices is a term that only exists, to my knowledge, in the Go programming language. But of the two, slices are the things that people use in Go rather than arrays, even though arrays are part of slices. And you'll see how that works in just a second. So what they are, both arrays and slices are things called data structures. Data structures are things that we study a lot in computer science. It's a way of organizing data, of course, as you could imagine from the name. But they have both of them share a kind of important characteristic. They can store large numbers of data items, but the important thing is that both of these storage things store items that are all of the same type. So you can have an array or a slice of integers, or you can have an array or a slice of strings. But in that array, you can't mix strings and integers. Okay? So everything in an array, or everything in a slice, we say is homogeneous. It's all the same. Okay? No diversity in an array or a slice. Everything in an array or a slice has to have the same type. And there's more to it than that, and we will be looking at that a little bit as we go along. In both arrays and slices, elements are accessed using brackets. Remember that. Brackets, not parentheses. The brackets on your keyboard, in here anyway, are located near the enter key, and they're lowercase, right next to the letter P. So we will be using brackets a lot. Every time we want to access elements of an array or elements of a slice, we use brackets to access them. You'll see how that works in just a second. The numbering in both arrays and slices starts at 0. There's very good reasons for that, but basically, if you trust me on this, all the formulas work out much, much easier if we start counting at 0. So the first element of a slice is numbered 0. The next one would be numbered 1. So I could have literally, and we will, 100 million elements in my slice. I can create a slice of 100 million variables and store different numbers in each one. It's the easiest thing in the world to do. The first one would be numbered 0, but what number it has in it is up to me. I can store anything I want in it. But it's numbered 0, and then the next one would be numbered 1, and then the next one would be numbered 2, and so on. No negative numbers in a slice subscript. I could store negative numbers in the slice. I could store anything I want. I have to set up the type for each slice that I create, but I start numbering at 0. Both arrays and slices take up what's called contiguous memory. Contiguous is just a fancy word for saying right next to each other. And this is important for you all to know. I'm assuming that all of you are going to become great computer scientists. I'm assuming that all of you are going to become majors, at least, and probably go on and become awesome in the world of computing. I really believe that. And for you, it is important to know that these elements get put into computer memory next to each other. Think of computer memory as a whole bunch of boxes that are all crammed up next to each other. And you can put stuff in each of the boxes. And they're numbered. You don't have to know how the numbering works, but it is important that the numbering is logical. Like this could be number 16, then the next one is 17, the next one is 18, and so on. And there's an easy way to get from one box to the next. You know how big each box is, and so you add the size to the previous address, and you get to the next one. You get to the next one. There's an easy way to get to any box that you want instantly. And the beauty of this with memory is that you don't have to go through all the ones that came before. If you want to be at box 900,000, poof, you're at box 900,000 instantaneously. You do not have to count your way up there. There is a way to instantly go to those memory locations. In this course, we don't have to worry about any of that. All we have to do is we say, I want to be at element 900,000 of this slice, and we're there. And the computer takes almost no time to do that. It certainly does not count its way through to get to that element. Okay, it just goes directly there.
So it's kind of like a game of Battleship or something? Or you just like...
Yeah, a game of Battleship is a good way to describe it. You say C9 and splat. It just gets that square. You don't have to count your way across and down. You just go right there and splat that square. Yeah. In memory, it's like that. You specify the address, and poof, you are there instantly. It's one computation to figure out where to go, and you just go there directly. And it is important to know that you do not go there by visiting every box that came before it. You can go directly there. As soon as you know where you want to go, there's a way for the computer to get directly there. Okay? So it's important that these slices take up contiguous memory so that I can do that. Now, there is an exception. I said the word usually, and that's because things get resized, and so parts of a slice can be in one part of memory, and then another part can be in another part of memory, and that just makes things a little bit more awkward. It slows down the efficiency just a little bit. But we don't have to worry about that. Finally, what's the difference between an array and a slice? An array has a fixed length when you create it. Okay? When we create an array, we will have to say how big it is. Slices, we end up with a size when we start, when we create a slice, but then that size can change. With an array, the size of an array will never change. Once you've created an array to be of a certain size, it will never, ever be any bigger. If you need it to be bigger, you will have to create another array, copy everything over, and then you can kill the first array, which is a pain, obviously. So why do people use arrays? The answer is they don't. They use slices. But every slice is really built on an array, and that's behind the scenes. And you need to know that because there is some overhead involved, and that when you define a slice, you'll see that you have to actually say something about the underlying array, the array that makes up a slice. So, bottom line here, it's often good to associate a slice with an underlying array so that you can control how often it has to be resized. With a slice, it will automatically resize, but when you get to be smarter, when you know more about what's going on under the scenes, behind the scenes, you can say, I want the underlying array to be this big and not whatever the default is, because you might know enough to know how to make it better, how to make it faster. It's like if you work on cars, right, and you tune engines to make them really, really good, you know what the manufacturer says about what the tuning should be, and you might know enough about cars to know that for what you're doing, you might want to tune it a little differently, and you might get better performance because you know better based on what you're trying to do or because of modifications that you've made to the engine. So it's important for us who know a lot about programming to be able to control how to resize a slice. For now, we don't have to worry about it because we'll let the system take care of us. But as we get smarter about things, we might want to change how it how often it has to be resized. Okay, so let's start with an array. We'll create an array just so that you know how this works and play with it a little bit, and then we'll throw this away and move straight to slices. So arrays are just like regular variables, except for the brackets, and the fact that we can create lots and lots of them all at once. Every array has a name. Okay, so in the example here on the slides, what do you suppose the name of the array is that is on this slide that you see? X. Very good. You got it all right. The name of the array is X, and we declare it in this way with the letters VAR. So VAR, and then what comes after VAR is the name of the array. X. Not a very good name, by the way, but it's short, easy, lazy way out. Okay, the next thing that comes in the declaration there is brackets, and a number in the brackets, and that number is the size of the array. And that array is going to have 10 elements in it, now and forevermore. 10 elements, no more, no less. Those 10 elements are created, and the last thing that you see on that line tells you the type. So obviously we're getting an array of ints, an array of integers, and there's 10 of them. And all of them are called x. I'm going to say that again, because it may not sink in. I have created, in this line, 10 variables, all of them called x. How in the world are we going to tell them apart? With what you called subscripts. I love it when you talk dirty like that. It's brackets. We're going to just say brackets and then put the number inside that we want. So let's go through and do this. I'm going to create an array of 10 integers. I'll flip over to the playground and do that. Whoops, that's the playground. There's the playground. So I need to create an array of 10 integers here. So here we go. Var x is an array of 10 integers. Okay? So we have created an array of 10 integers. They are accessed as x brackets 0, x brackets 1, x brackets 2, and the last one is x brackets 9. Does that make sense to you?
Yes.
What happened to x brackets 10?
It's 0.
X brackets 10 does not exist. X brackets 10 will give you an error if you try to look at it.
Why?
Because I created an array with 10 elements in it. Starts at 0, so let's count them off. x0, x1, x2, x3, x4, x5, 6, 7, 8, and 9. That's all 10 of my fingers, for those of you who can't see me. But that's all the elements that are in the array. Now I can print them off. Here, let's print one of them. Instead of saying hello playground, let's just print x sub, pick a number, 5. So let's print x sub 5. What did it print? 0. Because what's in x sub 5 is 0. How come? Because Go will initialize all numeric variables to 0. Go does that for you. All numeric variables will be initialized to 0. So all of those elements of the array right now, you can check this out. X sub 0 is 0.
You haven't assigned, like,
I haven't assigned anything to them yet. So Go has already done that for me. It assigned 0 to all of them. What about x sub 10? What do you suppose is going to happen?
Undefined.
It says invalid array index 10. Out of bounds for 10 element array. Does that make sense? Okay.
it's 11. There's not 11.
All right. Now notice that on this slide, I said that they're initially set to 0 by default, but look at the bottom line. You can set them the way you can a regular variable using an assignment statement, and setting equal to. So I can make x sub 7 equal to 99, for instance. So before I print them, let's just say x sub 7 equals 99. And now I'm going to print x sub 6. What's the answer going to be before I run it? If I print x sub 6, the answer is 0, and it is. And x sub 7
99.
better be 99. Make sense? Now, let me show you something nice that Go does for you that other languages will not do for you quite as nicely. I can just say print x. What kind of thing is x?
A variable.
It's more than just a variable. It is a variable. It is an array. It's a complex data structure. So when you print x, that's not exactly obvious what's supposed to happen. Go has a default thing that it will do, and this is it. It will show it to you in a certain form. And that all makes sense, doesn't it? Shows you brackets, and then it lists all the elements. Danger, danger. Do not do this very often. Certainly don't do this if there are hundreds of millions of elements in your array. That would be a bad idea. Well, it could make your screen get funky. It can do bad things to your screen. So just don't do it. I will try to keep you from shooting yourself in the foot, but basically, know what you're going to do before you try to do it. Okay, let's move to slices. I said I don't want to spend much time with arrays because we're not going to use arrays that much, but arrays are part of every slice. Slices can be created in a whole bunch of ways, and you need to know all of them, unfortunately. So here we go. The first way is to list the initial elements of a slice, and that's what this does. I can create a slice by saying x colon equals. Now I'm using the short declaration operator. X is a variable, and I say colon equals, and we don't know yet what it is, but the next thing that happens is brackets, open and close brackets. So this tells us that we're talking about a slice. So I read this in English by saying x is defined to be a slice of integers containing 1, 3, 5, 7, and 9. So I'm just going to do this in code here. So I'm going to get rid of all the stuff that I had there and just say x colon equals, x is defined to be a slice of integers containing, in braces now, 1, 3, 5, 7, 9. You don't need the spaces after the commas, but you do need the commas. And now if I print x, you see 1, 3, 5, 7, 9. My slice has 5 elements in it. X sub 0 would be x sub 0. Oh, sub. This is, it would be 1, yeah. I say in English sub, x sub 0, using subscripts. Yeah, but we're talking about the particular position in the array. So instead of saying x brackets 0, we usually say x sub 0, because we would write it in other terms, we would write it with a subscript. But, yeah.
So what's the, is this like a more efficient way to create an array? Because it creates an array and a slice at the same time. Right?
It creates an array and a slice at the same time, it does. But we don't talk about the array so much. The array is part of the slice. It's now, it makes up the slice, but we don't have to worry about it anymore. We just refer to the slice. What will happen, I'll jump the gun here a little bit on what the slides say, but what will happen is I can add more stuff to this slice and make it get bigger, which I could not do with an array. Okay. And every time I do that, the underlying array will actually get bigger. It'll probably double in, well, it won't double necessarily, but it'll jump in size. And we don't need to worry about it, it just does it. And in a minute, you'll see exactly how that works. All right, so this is just one way of creating a slice. Here's another way of creating a slice. We declare a variable called x. See that? We've got a variable called x, but we've got brackets right after the x and before it. So this says x is not just a simple variable, x is a slice. And it's a declaration, so we've got a slice with nothing in it. Let me just do that. All right, so I'm going to get rid of this, and I'm just going to say var x is a slice of int with nothing in it, and print it out. What do you think is going to be printed before I do it? X is a slice. How many elements are in it? 0 elements, so when I run this, it just prints brackets with nothing in them. Doesn't that make sense? back to the slides, notice that you can append elements by using this append function. Append is a built-in function as part of Go, and I will caution you right now, append is very, very tricky. So I will talk about append more, and in fact, I'm not going to do it. I'm not going to do this right now. We'll put this off and spend much more time on append in just a few minutes. Let me go show you the rest of the ways that you could create a slice, because there's more. I can use a special function called make, and I really want to illustrate this function for you right now, because this is when I want to talk about what's called the underlying array. With this, I'm creating a slice that has 10 things in it. But the actual capacity is 12. What does that mean? Well, remember I said that there's an underlying array? The array, which is not really visible to you when you're playing with slices, the array is actually 12 big. Okay, so you can have a slice by doing this that has 10 elements, but it really has a capacity of 12. So we got two numbers here running around. So one's called the length and one's called the capacity. So let's just do this. I'm going to say var x equals make. Let's read this in English before I type it in code. I'm not going to copy and paste. I'm just going to read it and then type it directly into the Go playground. We're declaring x to be a variable, and the variable is the result of the make function. Make is a function. And so the first thing that we want to know in make is, what is it that we're supposed to be making? And the answer is, read this with me out loud, a slice of int.
A slice of int.
Make a slice of int. That's what we're doing. Making a slice of int. And the capacity, or the length, will be 10, and the capacity will be 12. That's what make will do. So here I'm going to type it. Declare a variable called x, and it is set to what make, as a function, returns. Now I'll put the open and close parentheses here, and then inside the open and close parentheses, I need to put in what I had on the slide. Okay, so make wants to know, what is it I'm supposed to make? And the answer is, first of all, a slice of int. So we write brackets int. And then make wants to know two other things. It wants to know the length and the capacity. The length, I said, is 10, and the capacity is 12. All right, so if I do this and print it out, what am I going to see? A bunch of zeros.
10.
Very good. Only 10 zeros. Let's count them off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we have capacity for more. The capacity is 12. So what if I stuff another one in there? Which I can do with the append function. Then I'll have 11 things in there. What if I stuff another thing in there? Then I'll have 12 things in there. What if I stuff another thing in there?
It'll pop up error.
It will not pop up error. That's what you might think. That's a logical thing to think. But Go is actually set up to not do that, because it's slices we're talking about, not arrays. And a slice will automatically resize. So if you pop another one in there and you already had 12 things in there, you will now have 13 things in there, and guess what your capacity will be? 13.
Unlimited.
Not 13 or 14.
Unlimited.
Close.
24.
24.
It'll bump it up by 10.
It'll bump it up by 12. Because the capacity is 12. So it takes chunks of size 12.
Oh.
Anytime you need it, it just throws 12 more in there. So if you overrun the capacity again, it'll throw another dozen in there. Now what's so special about 12? Somebody made it up. I made it up. I made this slide up. that doesn't have anything real to it. It's just what I chose to do. But if you're smart enough to know things like how big a chunk of memory is grabbed at once by the computer when it does anything, the word size is what we usually talk about there, then you make that number the word size, and you get super efficient in terms of getting other access to this. So this is where I'm talking about how you can tune this program to be super, super fast by choosing that capacity just right. Now, most of the time you don't even have to worry about this because, in fact, I think, if I'm not mistaken, you can take that 12 out entirely. Yeah. And then it just uses a default. And to tell you the truth, I don't even know what the default is. But you can set it up to be whatever you want. You can make it like 100. Okay? It's still gonna give you 10 elements, but it's got a capacity of 100, so it will not fill the array underlying it until you've actually stuffed 100 things in there. And then if you stuff 101 things in, it'll just give you another 100 elements. That's how it works. Yeah.
Does it change in like the base code? Does it replace your value of 100, or it just will?
Nope. Nope. As far as your programming is concerned, nothing changes. This is all behind the scenes. It couldn't be better. It's just good.
Okay.
All of these slices will resize when necessary, but the last one will resize in clumps of 12 at a time because we got to control it. We set the capacity. Okay? Here are some useful functions, and we're going to use the first one for sure. I don't know that we ever really need the second one, but that first one is used over and over and over again. I'm sure I will use it today at least several times. The first one is len, the length function, and it returns the length of the slice. Now this may seem like a stupid thing. Didn't you know the length when you created it? Well, yeah, but if you keep stuffing things into it, then you might lose track, right? So, yeah, it's important to know what the length is. Or, if you're writing a loop that goes through a slice, you need to know how long the slice is so that you set up the loop just right. Okay, so you can say len parenthesis x, and that returns the number that is the length of the slice. Okay? Cap returns the capacity. I'm not going to worry about that, but I do now want to talk about append. Append is tricky, but append is very, very useful. And we'll talk more about append later. There's more that I'm not going to tell you today about append that I'll tell you another day. But right now, here's what you need to know. Append takes the first argument, the first input to append, has to be the name of a slice. Following the name of the slice is a comma, and then values that have to be stuffed into that slice. So, append is a function that takes at least two arguments, the name of the slice, and at least one thing to be put into that slice, and it returns a slice consisting of all the values in the original slice with the other specified values tacked onto the end. But the original slice is not changed. This is the tricky thing. I have burned myself on this so many times by assuming that when I say append x 567, that x changes. X does not. What happens is you get a slice that's returned which consists of everything that was in x with a 5, 6, and 7 stuck on the end. And I already told you about the bottom line there. Slices and arrays can be printed entirely by just specifying the name. Now I think I have something for us to try at the end of this slice. But I just want to go through this append function so that everybody knows. Remember that append returns what kind of a thing?
slice.
A slice.
Value.
A slice. The first argument of append must be a slice. The remaining arguments are values that will be added to the end of the slice, and the original slice is not changed unless you assign to it the returned value of the append function. So let's walk through these, and I'm going to type these all into the Go Playground, and you can too. But walk through this and tell me what's going to happen. First line, we'll read it in English. I'm creating a variable called x that is a slice of integers. So we get a slice created. I don't know how big it is, but it's as big as I want. But right now, there's nothing in it. If we printed it out at this point, and we saw the brackets with nothing in them, right? Next, print x, brackets with nothing in it. Next, x changes to what append does to x sticking 17 in. And then we print x. X has changed. So what was it? Before it was nothing. Now it should have 17 in it, right?
All of them are 17. Right?
No, this just sticks one number, 17, into x.
So like if it's an array of or a slice of 10, so then it will be like the 11th one is 17.
Then it would be the 11th one, yes. It just tacks it onto the end. This original slice had nothing in it, so this 17 just becomes the first element.
Okay.
Now I've got another append in the middle of a print. This gets tricky. In the middle of a print is this append, which takes x and wants to tack on 20, 25, and 30. What do you think is going to be printed as a result of this print? By the way, Professor Glass loves to ask questions like this on a quiz. So he does this, 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 and this. Forget the bottom line. What's going to be printed as a result of that line only? 17, 20, 25, and 30 is correct. That's what we've printed inside brackets. And now the trick question. We're printing x. What gets printed as a result of the bottom line? 17. 17 is right, because x did not get changed. So I want to go through and do this step by step, right? We'll flip to the playground and do each of these things. First, we'll create a variable x, which is a slice of int. And go ahead and print it. And to no one's surprise, I hope, we get brackets with nothing in them. So far, so good. The next thing, append 17 to x and stuff the answer back in x. You see how I'm reading this? Append 17 to x and stuff the answer back in x. If I didn't stuff the answer back in x, x would not change and it would still be an empty slice. But because I'm stuffing 17 into x and appending it that way, and append returns the slice that is the result, that returned slice will be put into x.
Wait. Can you say that? Can you
Yes.
say that one more time?
Yes. X is a slice that has nothing in it at the moment.
Yes.
This append will stick a 17 into it, but will not change x. It'll create a slice with 17 in it from x and just hold it there. X is still whatever x was. But because x is assigned whatever this did, this returns that slice that it's constructing. And that returned slice replaces whatever x was.
So if we had like variable x slice integer, and then the brackets like 1, 2 or something like that, and then you added the x onto the end, would that mean it would be 1, 2, and then 17?
Let's do it. Yeah.
Because
If we do this and put 1, 2 like this.
Yeah.
No, it doesn't. It doesn't like that because If you remember back on the previous slide, to create a slice, we'd have to use the other shorthand thing.
Oh,
We can do that.
okay.
So instead of doing this, we could do this. X colon equals a slice of int. So now we've got 1, 2, like that.
And
We can do
then
that.
If we do the
Append.
append after it, it'll do whatever that value is, but it'll.
Now, do you want to print it like I'm doing here, or do you want to assign it? Do you want to assign it to X?
Yes, and then print it after.
Okay, so append to X, what? 17?
Yeah,
Is that all?
sure.
Okay. And then you want to print the result. Like that. Print X. Okay, X will change. This is saying, this part right here is saying that X is going to change. And it's going to change to whatever append does. And append will stick 17 onto the end of X. And so X becomes a new slice, which has whatever it had in it before, plus 17 on the end of it.
Yeah, so it should be 1, 2, 7. Oh, it shows 2 of them.
Well, because we're printing twice. We asked it to print.
Yeah.
We asked it to print there and there.
Okay, yep. That makes sense.
So far, so good? Okay, so if we go back to what we had before, we had a slice with nothing in it. So let's just do that. Can I do this? Oops. You have a slice with nothing in it, then I stick 17 in it, and now I'm going to do what this slide says, print appending X 20, 25, 30. So print append to X, I forgot what, 20, 25, 30. 20, 25, 30. Like that. And print that. So it shouldn't surprise you that this is what prints 17, 20, 25, and 30. But what might surprise some people is what's going to happen if I print X.
It'll go 17, 20.
Nope. Just 17. Why?
Because you.
I did not change X.
Oh,
Matthew?
I was gonna say. So because you set X equal to the 17, that's the only reason why it comes up.
Because I appended to X 17, that stuck 17 into the slice that had nothing in it from before. All right, let me do this a little more simply. All right, variable X brackets int. In other words, variable X is a slice of integer. I have said nothing more. Therefore, X has what in it? Nothing in it. Nothing in it. It's a slice that has nothing in it, but that can hold integers. Right now, it has nothing in it. If I print it, I get an empty slice printed. That's what the first brackets are, a slice with nothing in it. I can then start appending stuff into it. I can append any number of things that I want. 17, 18, 19, 189, whatever. 0, 2, 6, whatever. And all of those things get stuck into the slice. And then I append 20, 25, and 30 to the end of it. But because I did not change X here, X didn't get changed, and X remains what it was before.
So there is no colon for X, it's just X equals.
X equals, yeah, because X has already been defined.
Okay.
Colon equals is a shorthand for define X and set it.
How long does it hold it like that? How long do you...
It holds it that way until you change it. It holds it forever until you change it. Okay? Onward. Slices and arrays work beautifully with loops. We're going to try some exercises. These are the routine things that you need to do. I have analogies with sports here. If you're an athlete of any kind, there are drills that you have to do to perfection. Sometimes the drills don't have anything to do with your sport. You know, you just have to do 5 push-ups, right? Just do 5 push-ups, and you just do them. Well, this is like do 5 push-ups, except it's easier than that. 5 push-ups is hard for people like me. But increase all the elements of a slice by 1. Let's set up and do this problem. I'll create a slice with a bunch of stuff in it. So here's a slice with nothing in it. Change it so that it now has some numbers into it. Let's put some numbers in. You get to pick. 5, 25, 11, 0, negative 40, 13. Okay, that's enough.
I thought they can't. Or maybe.
Oh, I can put any integer in there. I can't refer to a negative subscript. I can't say x sub negative 1.
Oh, okay. Yep, that makes sense. I got it.
Okay, so if I print out x, I don't think anybody should be surprised about this. Does that all make sense?
Yeah.
What about x sub 0? What's that going to be? 5? Everybody agree? X sub 5, without printing it, what's it going to be?
13.
Wait,
X sub 5.
Error. That's not be there.
not error.
X sub 5. Well, let's count it off. This will be x sub 0. This is x sub 1. This is x sub 2. This is x sub 3. This is x sub 4. And this is x sub 5. 13.
Oh.
You were right the first time. X sub 5 is 13. X sub 6.
0.
0 and expanded.
Nope.
Or 6.
Because we created the slice, and at the moment it doesn't have anything in it but those elements. We could add another element into it, right? We could say x equals append onto x like 99. And now we can do it.
Oh.
X sub 6 is 99. X sub 5.
So that will not extend. It will not automatically.
It will not automatically extend the slice unless we append something into it. Okay? I can't just refer to what's off the end of the slice. The slice is still considered to be, oh, okay. How long is this slice? Let me get rid of this a minute. And instead of printing out this, let's print out len of x.
The length of
The length of the slice x. And it says 6. 1, 2, 3, 4, 5. There are 6 elements in the slice. If I do x equals append x 1, What's it going to print now?
7.
7. Okay, you see how that works?
Yeah.
So if I try to go off the end of the slice, it's going to give me an error. Even though I can go ahead and keep appending anything I want. X equals append X. It does that. It just appends it. If I say append, it does it. No error. And it keeps stuffing more things in there. But I can't refer to something that is off the end of the slice. Okay.
Just print it in the printing, making the size not change, right?
Say again?
And if you print it without like signing it to the variable X,
Oh, yeah. If I print it without assigning it to the variable X, like this, like that, then it's printing this big long slice, but X has not changed its length. Correct. Does that all make sense? Okay, now what I was saying though was, let's go back to this, the original situation here. And the problem said, remember the problem? Increase all the elements of a slice by 1. Increase all the elements of a slice by 1. So let's do that. To do that, we're going to need a loop. And I'll use my loop variable to be n, starting it at 0. Now, this is a pattern that I want you all to learn. This pattern is one we use whenever we work with a slice or an array, and we plan to go through the whole array. Where does the array start? At which element?
0.
0. So we start with n set equal to 0. The next part of the pattern will always be the same as well. How long do we continue? We continue as long as n is less than the length of the slice. So just memorize that pattern. Start with 0, continue as long as x is strictly less than the length of the slice. And then increment n. Okay, now I'm going to show you some coding practice, some coding trick here that people often use when they don't have a very sophisticated development environment. This is a playground. It's not that great, so that when I type an open brace and hit enter, it doesn't automatically give me a closed brace. So what I will do before I ever do anything else is I'll hit another enter and put the closed brace in, so that syntactically I'm doing something that's correct. I've got an open brace and a closed brace. Same thing for open and closed parentheses, open and closed brackets. I usually will type both when I start and then stuff in what I need. Okay? All right, so I need to go through this slice, and what did I need to do? The slide said increase each element of the slice by 1. All right, what's the name of the slice? X. Which element has to change? X sub n. That's very good. X sub n, where n is 0, 1, 2, 3, up to but not including the length of the slice. Length of the slice would be off the end. X sub n, and what do you want to change it to? X sub n plus 1, which we could write in another way, but I don't want to do it right now. X sub n is set equal to x sub n plus 1. Increase x sub n by 1. So we can do this, and if you run it, well, nothing will happen because, well, something will happen, but we won't see it. I have to print it. Very good. Let's print it. And I'll print all of x, and so we get a before and after picture if we do this. Here's before, and here's after. Run it. Isn't that a beautiful thing?
So,
Yes.
the program that you just wrote just adds 1 to the end of each of the numbers.
It adds 1 to each of the numbers that's in the slice. Did you see how that worked?
Yeah.
Okay. So tomorrow we're going to do a lab on this. I've actually already posted it, so if you want to play with it already, you can play with it. Tomorrow we may not be here. If classes get canceled, we'll send you email and tell you what you should do. Okay? I've finished recording.